chapter 12 material. Alright, so we started this discussion of digital alkenes and looked at the XY and the energetic bond enthalpies that of course determine the thermodynamic preference for an addition across the pi system in alkenes. And you can look at this more specifically with the numbers that are tabulated in table 12.1 in the textbook. So then we started with the addition of AHX, hydrogen fluoride, across a double bond, and I introduced you to the rule of Markovnikov. So today we'll go down in the list here. We'll look at the radical mechanism, which is anti-Markovnikov. Again, it's mechanism-based, just the outcome is the opposite product you would expect from application of the Markovnikov rule. However, it is consistent with the overall mechanistic picture in terms of the stability of the reactive intermediate. We'll then just very quickly look at the transformation known as the Wacker oxidation or the Wacker reaction, which is an industrially very significant process. We'll do a couple of acid-mediated additions, the sulfuric acid and the general acid catalyzed hydration of alkenes that gives us alcohols as a product. And then we'll go into the biggest chapter, maybe a single part of this chapter 12 is the addition of halogens. And we'll do a bromination reaction and discuss the bromohydrin as well as the stereospecificity of this reaction. Then we'll go further into hydroxylations using osmium tetroxide, potassium permanganate, and ozone. And that's probably where we're going to hit the end of today's class. So this is kind of our list of specific chapters or topics today. So let's get started with the radical mechanism of the addition of HCl across propene. And I've already given you the general equation as well as a few key points. So the reaction starts with propene, uses HCl, and the key is the presence of a radical initiator. And we've seen that this is dibenzoyl peroxide, which you only need in catalytic amounts, small amounts, and that gives you the terminal fluoride, the terminal halogen. And the hydrogen has added at this position here. So we now have an anti-Markovnikov product because the hydrogen is added to the more substituted part of the original alkene. So again, this is a hallmark for anti-Markovnikov. Okay, so let's look at the mechanism. And I already told you this is a radical chain. So this is different from the ionic addition, where you have carbocation intermediates. That was discussed on Tuesday. So make a note here that this is a radical chain mechanism. And that is, of course, the reason for the opposite regiochemistry in the addition. And like any radical chain, you have to have an initiation. And the initiation starts with the formation of the first radical from the dibenzoyl peroxide. And that is a reaction that can be initiated with photochemistry, with light, or also by heating, because dibenzoyl peroxide is a thermally not very stable compound. So we can do light, H2, or we can do some heating of the reaction mixture. And that leaves the central bond, the weakest bond, which is the bond between the two oxygens. And it generates, through this homolytic cleavage, our first radical. And usually we can formulate the mechanism as a radical chain starting this radical benzoic acid radical. But I would like to point out that this by itself has an additional pathway that is actually quite favorable, occurs quite readily, because of the formation of carbon dioxide. And so this benzoic acid radical can, through this radical cleavage mechanism, denote the single-handed arrows that I use for radical pathways. So this can collapse to give a phenyl radical. And the outcome in the propagation steps or initiation reaction is the same. We have generated a radical, and so we can now continue in the actual chain process. But it can be the phenyl radical, or it can be the benzoate radical. So what I'm going to use right now is just the benzoate radical, but again, it's a possibility that the phenyl radical does something very analogous if it is formed through decarboxylation. Depends a little bit on how you generate these radicals. As you might imagine, since CO2 is a gas, if you do this by heating, there's a greater chance that our initial radical is going to kick out the gas here, and that we form the phenyl radical through a continuous initiation. So this reacts with HCl via a hydrogen atom transfer reaction. It extracts a hydrogen atom and leaving us with a chloride. So in this case now we generate benzoic acid plus the Cl dot. So now we have finished our initiation. We have a radical that can now initiate the propagation steps. So in the propagation reaction, we're now working with our chloride and, of course, our organic substrate, which is the propene. And they react. Chlorine adds onto the pi system, and it forms the more stable radical preferentially. And of course, the more stable radical is the secondary radical. So I don't want to add in the center at the two position of the propene, because otherwise I generate a terminal, a primary radical, which is less stable than the secondary radical in the pathway that I just drew on the board. So we get this radical, again it's a secondary radical. And again it's stabilized. To some extent, radical stability follows somewhat carbocation stability, so tertiary radicals are more stable than secondary, which are more stable than primary radical. And so this preferential formation now immediately explains our regiochemistry of the overall addition, because now I have a reaction with additional HCl, and I transfer my hydrogen now, hydrogen atom, and I regenerate the Cl dot, which of course carries the propagation steps. So this Cl dot then of course reacts again in this chain reaction pathway and starts at the top here. It's the first equation. Okay. And so the chain keeps on going until it runs out of components, so until it either uses up the HCl or the propene, until one of the species is present in very low concentration and is exhausted, and continues to lead to the product here, which is this terminal chloride. So again, the regiochemistry is overall anti-Markovnikov, because the hydrogen has been added to the more substituted carbon. But the mechanism has changed slightly, and so in the intermediate, what we notice is we still form the more stable reactive intermediate, which is in this case, of course, the secondary radical. So just a slightly different mechanism, but the same fundamental principle. Any questions for the radical addition of hydrogen chloride onto alkenes? So it's our first case that we can see that we can actually determine by the addition, in this case, of a radical initiator, what product is formed preferentially. We can form either regioisomers by either an Markovnikov or an anti-Markovnikov pathway. So let's look at some other radical processes. So again, industrially important is the polymerization of olefins. So ethene is a very significant feeding stock for a lot of consumer goods, plastic bags and so on. And we generate polymers through radical polymerization. In this case, we often just use the peroxide. It could be dibenzoyl peroxide, it could be another compound where you just have a relatively weak heteroatom signal bond. And the initiation here occurs through heating, as well as in the presence of a lot of ethylene that is compressed. So we usually do this at about 15,000 psi. So a lot of pressure. So a high pressure reaction in a reactor system that then leads to a formation of a polymer, a solid material that has a very high molecular weight. So we get from this process what I call polymer chain, and this is polyethylene. And N is pretty large, so N can be, 100 or more different ethyl molecules, and so they interact and form this tractable polymer that can easily be injected into all kinds of shapes, and it also can be nicely extended. So again, the mechanism is that of a radical polymerization. And so if we just look at the propagation step, we have a formation of an atom. So from our oxygen dot radical that is added onto an ethylene molecule, we generate, in this case, this primary methylene radical, and that acts with another equivalent of ethylene, and it essentially just combines with the pi system and generates a larger compound. You can see how the chain here grows. So then this radical that has now already added 2 ethylene monomers adds again to more ethylene, generating an even larger system. So if I count now my CH2 groups, I already have 4 of those. And then I end up with one that carries the radical. And so in this process, this then just continues as long as there is ethylene, and it generates the polymer. Okay, and so just the nomenclature here, this system would be our polymer. And the actual ethylene is our monomer. And so this is a reaction that gives this simple monomer, ethylene, readily available as an industrial feedstock, and it generates polyethylene, a polylate structure. Lots of ethylene groups, very large chains by this radical polymerization process. So all the monomer units are pairwise or sequentially built into the polymer, and it grows until there's some kind of a termination step. So the termination reaction can be any kind of hydrogen atom abstraction from the environment, or recombining. Two chains can recombine. So a typical termination of the chain would be when two of the monomers actually combine. So you can have so we can have different lengths of the radical chains. So one can have X of the methylene groups here, the other one can have Y. And these can now combine. And that will give us a system that is now terminated. Because it doesn't have a radical anymore that can add to another ethylene molecule. So this is one of several possible terminations of the radical chain. Depending on how many X and Y's you have, this could be a very large molecule already before these two strands combine. And there are the termination steps, but this again also revisits the radical reactions that we had earlier in the term. So again, keep in mind the propagation steps and the initiation steps, and then also the termination pathway. So they're typical for a radical chain reaction. Any questions regarding the ethylene polymerization? This is one example of the formation of a large molecular weight organic molecule through a repetitive insertion of a functionalized monomeric unit. And we exchange the pi bonds in single bonds to single bonds in this process. Okay, let's look at another application of ethene. Also known as ethylene gas. So ethene and ethylene are both just just a simple, just a fundamental double bond here. 2 carbon. Feeding stuff. So another application in industry is the Wacker process. And this involves the use of ethylene in a system that contains dioxygen as well as water and 2 catalysts. So we now have a combination of a palladium salt, usually palladium chloride, together with a copper salt. This is an interesting reaction. The mechanism is something that I can actually discuss, for example, on Saturday, when we have our makeup class. I'll be happy if you have questions about the mechanism to show you the mechanism. For now, let me just show you what the initial product is in this reaction. You initially get vinyl alcohol. So formally, you replace one of the hydrogens with an oxygen atom that kind of inserts in the carbon-hydrogen bond. But that's not the real mechanism. The real mechanism is a little bit more involved. And again, I'll be happy to go over that on Saturday if you have a question for that. So this is vinyl alcohol. Now, vinyl alcohol is rapidly equilibrating, and in fact, thermodynamically preferentially equilibrating to another compound, and that is acetaldehyde. So the overall product in a Wacker oxidation, if you use ethylene as a starting material, is the formation of an aldehyde, in this case acetaldehyde. So we keep the number of carbons, stays the same, but as you can see, we exchange a hydrogen with an oxygen, and we also reshuffle a hydrogen to the, in this case, the terminus of the CH2 group here, so another hydrogen shows up here. So it is a catalytic process, and it requires the presence of actually 2 metals, and both metals have a specific function. So the reaction doesn't work all that well if you leave out palladium or leave out the copper. So you get very low yields, lots of side products if you don't have both catalysts present in the reaction. So the Wacker process, again, industrially important because you take a cheaper building block, ethylene gas, and then you generate a more valuable building block such as acetaldehyde. And of course, you can expand that to a lot of different alkenes that are converted to the corresponding carbonyl functions using this type of reaction. So this is just one application of, again, this industrially significant conversion reaction. Okay, any questions for the Wacker process? It's a little bit more complicated process. I'm actually not showing the mechanism on purpose because it involves a number of principles that are relatively new and something you can understand, but it's a chain of different intermediates. It's a little bit confusing, so you actually do not need to know the mechanism for the final exam. So this is not something that you need to know, but I'd be very happy to show you a mechanism. It's been well investigated since it's such an industrially important process, so that you just, you feel you have a mechanistic understanding. But again, it's not something that I expect you to actually remember. But you need to know what the reaction product is. So this is one of the few reactions I'll show you, and I'll just basically expect you to realize, you get these type of products because it is an important reaction. You need to know how to generate aldehydes. It's one of our processes that is useful if you need to make an aldehyde for a particular starting material that contains a double bond. Okay? Yeah?
What's part of the polymerization for
the olefin? It's also, olefin is a synonym of alkene. And it's an older expression. Olefin is an older word versus alkene. But since the polymerization actually was discovered prior to some of the other conventions taking place, it's often also referred to as an olefin polymerization. So olefin is just a synonym of alkene. And So sometimes I'm throwing out the words so that you learn a little bit more about the language. Like any language, you have sometimes several words to express something that's very similar. Okay, anything else? All right, let's look at the formation of alcohol. And so one of these processes is hydration of alcohol. And we're going to now look at two processes. One is the sulfuric acid addition. So sulfuric acid addition. We can add sulfuric acid across a double bond. And so what I can use as a simple example here is again, maybe just our propene molecule. So we can use propene and treat it with sulfuric acid. And I can now protonate the double bond. This is a reversible reaction, so it's an equilibrium. And depending how much sulfuric acid I use, you can get more or less of that protonated olefin. Of course, the protonated olefin is a carbocation. And the addition follows the Markovnikov rule because we have the formation of the more stable secondary carbocation. This is very similar to what I showed you on Tuesday. As a counter ion here, you have the sulfate. And so there's a recombination here between the two species, and that leads to the formation of a sulfate ester. So now from here on we can go to the alcohol by adding water. And water will attack the sulfur. So that's similar to a carbonyl addition because obviously the sulfur is very electron deficient because it is attached to all these electronegative oxygen atoms, including oxygens that have formal double bonds to the sulfur atom. So initially, again, I go very stepwise with this mechanism. I will have this charged intermediate. I can reshuffle the proton from the oxygen, originally from the water molecule, into the oxygen that was is attached to the sulfur. Neutral intermediate, so from the charged intermediate by the realignment of the or redistribution of the proton, I'll get this neutral intermediate, and now I can eliminate the sulfate and again transfer hydrogen onto the oxygen. and that gives me the product of this reaction, which is the alcohol plus I get my sulfuric acid back. And again, our product here is now the Markovnikov product, because we're dealing with carbocation intermediate formation of the more stable secondary carbocation. So this is the Markovnikov. Video selectivity. Okay, so that's just a little bit more involved addition of water ultimately across a double bond. Sulfuric acid serves as the intermediate nucleophile, but is then hydrolyzed in the subsequent attack of the water. So the reaction that continues with the attack of the water molecule, this would be our hydrolysis step. Because we eliminate the sulfate ester, monoester here, and we kick out the acid, which is the sulfuric acid, which we used to begin with. Okay, so it's a catalytic process in sulfuric acid in the presence of water. So that's a sulfuric acid addition that leads to the formation of an alcohol. In this case, it would be isopropanol from propene. We can also generalize this into an acid, general acid catalyzed hydration. Particularly if you use non-nucleophilic acids, then the acid would not participate. So if I use the same example, but now I'm using a very non-nucleophilic acid, for example, perchloric acid. So this is perchloric acid. Then again, I would protonate my double bond, formation of the secondary carbocation is more stable than the primary carbocation, and now I have a ClO4 minus. This is perchlorate as a counterion. And perchlorate is non-nucleophilic. So there's no addition process until there's water. And this would be, of course, a reversible reaction. But if water comes into play in the same fashion, I can now get a direct addition of water. So I bypass the whole hydrolysis step. And now the perchlorate is just absorbing the proton. And so in this reaction, I get my alcohol, same alcohol, this is the isopropanol, plus I regenerate the perchloric acid. Okay, and so the perchloric acid is the catalyst. Catalyzed hydration. So whatever I put in originally as a catalytic amount of acid comes out when I transfer Okay, so this example is just another variation, but it actually nicely illustrates, again, another principle that you've seen many times. You can get different pathways, even if you get the same product. So a reaction that looks very similar can have a different mechanism depending on the nature of the intermediates that are involved. So both sulfuric acid and perfluoric acids are acids. They transfer a proton. That's the important initial equilibrium reaction that activates the alkene. And both lead ultimately to the same product. But the sulfuric acid mechanism is considerably more complex because you involve the sulfate ester that's then hydrolyzed to give you the alcohol. Okay. So if you actually study this reaction, you will see different intermediates and different side products. In the perfluoric acid pathway, we have initially the same carbocations with bromination, but the perfluorate is non-nucleophilic. It is not a good nucleophile. It's a very bad nucleophile. It's highly delocalized. Just doesn't want to have an oxygen attack in the carbocation, so the water is now faster and intersects the pathway, leading directly to a protonated intermediate that can donate back a proton and regenerate the acid. So this is an easier process, a faster process maybe, depending on how the equilibrium is and these different reactions go, but clearly a simple mechanism leading to the same overall product. Okay, so you can appreciate a little bit of the complexity sometimes that these reactions pose, because even if you have the same product, the same starting material, a very similar mechanism, there really is no, not always a proof of any way that you have the same kind of intermediates in your reaction. Partially they're the same, but then others are not duplicated because they use a different reagent. So now, of course, also, before I complete this and move on to our next discussion, which is the bromination of alkenes, let me put in a box here a very important comment, and that is in all of these pathways, you have to keep in mind that the carbocation intermediates can rearrange. So remember here, note something that we've looked at in a number of other cases before. The carbocations can lead to rearrangements, for example, Wagner-Merwein rearrangements. So the carbocations can rearrange that we form in these hydration reactions if you can form a more stable carbocation. So if you can go from a secondary to a tertiary carbocation by some kind of a shift, either a methyl group shift, a carbon shift, a hydride shift that we've seen, then you can get different products by a backbone rearrangement. So you have to keep that in mind, again, when you think about the mechanism. In this case, there's no obvious way to generate a more stable carbocation. So I use a simple example to illustrate the principle, but if you have a more highly substituted system, these intermediates could rearrange maybe and form a tertiary carbocation, and then that would be a competitive pathway that might give you, again, another product. And so by the selection of what acid you use, you might actually be able to influence the rearrangement, maybe trap the intermediate before it rearranges, or have a complete rearrangement taking place, and so on. Okay. So there's lots of ways to manipulate the reaction so that you get different products. Okay. All right, so that kind of concludes these simple additions, protonations, and radical additions on alkenes. And so we'll look at the bromination reactions. But are there any questions for the last two boards here? Anything that doesn't look quite obvious to you? Yeah.
After sulfuric acid donates is that a good nucleophile, HSO4, or does it take a while to react?
Yeah, so what are the rates of the different reactions? That's a very good question. So it depends a lot on what else is in it. Rates are always relative, right, in terms of a competitive reaction. And so the sulfuric acid is usually used in quite some excess. It's really rarely used catalytically. If you were to use it catalytically, probably a lot of the water would be just as fast adding in there. But if you use something like 85% sulfuric acid in the reaction mixture, then it's the majority of the components in there are actually sulfuric acids, and so the sulfate is very competitive. So the reaction is relatively fast. to give you an idea, it's probably something that is 10 to the third, 10 to the fourth, or even 10 to the fifth percent. So it's relatively fast. The water addition is similar, but it depends a lot on how you're doing it. And so in the lower process, not only do we have a very non-nucleophilic acid, so that would be, let's say, 1 million times slower than the sulfuric acid. So that's a huge difference. But we also use small amounts, we use it catalytically, so there's not much of the perchlorate around anyway. And so the water has no problem to intersect.
Okay, so you're saying that the water is much slower than the sulfuric acid?
The water would be much slower than the sulfuric acid, mainly because there's a little bit of water, there's a lot of strong sulfuric acid, so the water is to a large extent protonated, H3O+. So there's actually not much of the H2O in there. So that's one other aspect that makes a difference between the two processes. And there, keep in mind again, if you compare relative nucleophilicity, if a species has a charge, a negative charge, it's generally a better nucleophile. So that is an advantage for the HSO4 minus in the addition versus the H2O. Right? We have a negative charge on the sulfur. Okay, let's look at bromination. So why is bromination such an important chapter? Well, because it has a lot of a good understanding of the mechanism, and there's a nice summary of some of the processes that are going on in the conversion of an alkene into a different organic product, more highly functionalized organic product. So the bromination is generally one of the major parts of the alkene chapters. So this is an important mechanism. Again, I guess again what I'm telling you is now bromination is definitely a mechanism that you want to practice and you want to know about. Okay, and let's use cyclohexene for this purpose. So I treat cyclohexene with Br2, and I end up with the dibromide. And let me go straight into the mechanism here. So again, our pi system reacts. In this case, it reacts not with an H in the reagent, but with a Br as part of the Br2. And the Br, the second bromine, serves as a leading group in the reagent, so it generates Br minus. And this is again a reversible process. And so what I formed is a species now that's a little bit different from the proton addition, so that's a major distinction. I formed this interesting 3-membered charge species, and I put the positive charge in this particular resonance structure onto the bromine. Also, this is an addition across the pi system. So obviously, I maintain the geometry, and so the two hydrogens are, since it is a Z-alkene, the two hydrogens are pointing in the same direction, which now, because I have a formal sp3 hybridization on these two carbons, would be down, and the bromonium ion here is up. But of course, this is one of the two enantiomers that I can draw here. The other enantiomers with the bottom intact would also be formed to an equal extent. So this is our bromonium ion. And so the bromonium ion, of course, is an activated species, it's a charged intermediate, and it has a counter ion, which is the Br minus. And it's transiently formed. And you can easily see the formation of these species if you add Br2 to an alkene. The Br2 is brown, and then the bromonium ion is colorless. So you decolor it very quickly, you form quite a bit of this bromonium adduct. There's a picture all about that shows you that, just a static picture that illustrates the decolorization. So these are activated bonds. And so here we can now do a substitution reaction. Since it's symmetrical, it doesn't matter where I attack. For this species, we'll look at another one where it does matter, and I open this up. So now our product, neutral species now, has a defined configuration where Br2 is added across the double bond, and I get the trans product. So this is the bromination process, and it has a defined stereochemistry due to the presence of the intermediate bromonium ion, which then undergoes an anti-attack. So this is an SN2 process, or backside attack. On the bromonium ion, on the carbon of the bromonium ion, I get the trans dibromide in my product. And so now if you compare this pathway to the protonation, we obviously don't have a carbocation, at least not formally. It's not formally the same. But we do have a bromonium ion where the bromine still mainly has the positive charge. He has added to both ends of the double bond, so a different mechanism again. And then it is collapsing by an SN2 attack of the counter ion here, the Br minus, that leads to the neutral product. And thermodynamically again, you can calculate the bond energies, the bond enthalpies, and we can find out that this is a preferred process. So overall, thermodynamically, this is an exothermic process. Because the subsequent reaction here essentially is preferred and irreversible. So this is a reaction that clearly leads to a preference in the product formation. So one aspect of the bromination that makes it attractive is the fact that it is stereospecific. And stereospecific is an important noun here. It's an important expression for a mechanistic consequence of a particular pathway. So stereospecific means that if you start out with one particular stereoisomer, we get a very defined stereoisomer product. Defined stereoisomer of the starting alkene leads to a single defined stereoisomer of the product. And I'll show you in a minute an example what that means for the alkene addition. Before I show you that example though, let me put down in parentheses another expression that this should not be confused with. Okay. And so what is the word that I don't want you to be confused with? Videoselectivity as part of that word. But if you keep on stereo, then it would be stereo-selectivity. So stereo-selective means something else than stereo-specific. So just note that, because it is very easy to get confused by this particular expression of stereospecificity or a stereospecific reaction. So if I refer to a stereospecific reaction, I have something very, very specific and particular in mind. And if I say something is stereoselective, it actually means something else. So stereospecificity is very absolute. It essentially means exactly this. You start out with one isomer of the starting material, you get a single defined isomer of the product. Stereoselective means you get a predominant formation of one isomer or the other. But the ratio could be 60-40. That's still stereoselective because one isomer is formed preferentially over the other. So stereospecific is very absolute. One isomer, one product. Another isomer, a different product. Here, you can get mixtures. So selectivity can be expressed in various ratios. Specificity is absolute. So it's an important distinction to be made. Regioselectivity, it can also be regioselective and regiospecific. So for regioisomers, you have a very similar distinction in terms of differentiating between something that's specific versus something that's selective. So you can transfer those between different types of chemoselectivity. But here, we are referring to an arrangement of groups in space. And so it's different from a regioselectivity. And I can again go over the difference later on, but let me first give you an example for what stereospecificity means in the context of the bromination reaction. So what I'm telling you here is that if I use the Z-alkene and I use the E-alkene, those are two different stereoisomers of butene. Okay. So the structures only are different in terms of the orientation of the two metal groups. They're either together or they're opposite the double bond. So these are two stereoisomers of the same material. And if the reaction is stereospecific, which the bromination reaction is, so if I do this with Br2, I will get distinct stereoisomers. Let me show that. So if I look at the stereoisomers that I'm getting, applying the mechanism of the bromonium ion, then from the Z-alkene, I will get a very defined dibromide. And then I'll look at the configuration. And here I have R. And of course, in the racemic mixture, I will also get the SS enantiomer. But in terms of the diastereomer I'm getting, it is only the RR. So this is chiral. So this is the chiral product, the chiral dibromide. If I do this reaction and follow the mechanism on the E-alkene, same conditions. What I'm getting now is the RS product or the meso product. So here I'm getting, if I look at the stereochemistry, the R, S. And I hope you remember to differentiate and to identify the chiral versus the meso compound. So this is the meso product. So there's no enantiomer. The enantiomer is identical. And so this is the meso. Okay. So in one case, I get the RS, which is the meso dibromobutane. And in the first case, with the Z-alkene, I get the racemic chiral dibromobutane product. So the selectivity, the criterion for stereospecificity is fulfilled here. So bromination is stereospecific because I can do the test with two different isomers of the same starting material, 2-butene. In one case, I get the chiral dibromobutane product. In the case of the other isomer, I only get the meso dibromobutane product. And so there's no crossover here. The reaction gives us a single product depending on the orientation of the substituents in space, the stereochemistry of our starting material. So again, this is a very important example. It's a kind of a subtype of a reaction of an organic process that is exemplified here as part of the bromination discussion, bromination of an alkene. And it points out the special feature of bromination, the fact that this is an example of a stereospecific reaction. And there's a bunch of reactions that are stereospecific, but this is the first time we actually formally introduce this. So when you look at this, make sure that you go through the mechanism for both of these products, and you come to the same conclusion that is on the board. And if not, make sure you ask this either in a recitation or again ask me in the next class to go over the actual mechanism for these two brominations. So keep in mind, when you do this, when you study this on your own, that you involve the bromonium ion and keep all the substituents, of course, correct and the orientation correct. And then you have to redraw it in the zigzag orientation, because I put the two methyl groups across from each other to show this conformation here. And then you should get from one alkene to the Z just this product and the enantiomer. In the other case, of course, you get this meso product where the enantiomer is identical or superimposable to the product. Okay, so very nice example. Again, this has a very high chance to show up in the next exam because it is summarizing both the bromination process as well as the kind of handling of substituents in a mechanism, reasonably complex mechanism where you have a defined intermediate that reacts stereospecifically to lead to defined single product. Any questions regarding stereospecificity? Okay, so make a note, make sure that you look at the mechanism yourself, try to draw it out, talk to colleagues about it, and if you have any questions, pick that up with the class TAs or ask me at a future lecture at the review session. We will have a review session probably depending on the availability of classrooms, which is a little bit up before the final, maybe on the weekend before the final week, but I'm not sure I can actually access the lecture rooms or might be other makeup classes at that time. So I'll keep you informed, but I definitely plan to have a review session. This could be also something you could ask. But in the meantime, just go to the recitations or go to the office hours, the fishbowl hours, and make sure that you do it first. And if there's any questions, that you have somebody help you from where you did a mistake. It's because this is really kind of a key part of the mechanistic discussion of chapter 1. Okay. We have a few more minutes. In this time, I would like to go to a related process, and that's the halohydrin formation. Okay, so another very closely related type of pathway, halohydrins. I'll show you what a halohydrin is. Since we're in the alkene chapter, of course, not surprisingly, I start again with an alkene. In this case, the 2-methylpropene or isobutylene starting material. And I treat this now with a mixture of bromine. But the big difference here, the important difference is that now I use H2O. I use water as an additional component. So this is a mixture of water and bromine. For the bromination reaction, we usually do this in organic solvents, hydrocarbon solvents, and so on, and there's no water. So this is something that we add new into the system to modify the pathway that we have seen in the bromination reaction on the left side of the board. So our first reaction, again, very similar. We add Br from Br2.